I've moved very recently back to the UK, but I'm going to talk about some work I did in the Sigman group in collaboration with Genentech, which is all about how we can balance representation of conformal ensembles of bisphosphine ligands in our library building campaigns. And those of you who are not terribly familiar with bisphosphine ligands, these are ligands which have two phosphorus, it's these two orange balls here. And what's really unique about it is you can change many parts of this. So you can change the backbone, which links these two phosphorus atoms around the back, or you can change the substituents, which connect to the other two bonds that phosphorus can form. And so this allows you to kind of generate lots of different steric and electronic types of bisphosphine ligands, and also generate chiral pockets if these groups are asymmetric. And one particular example where these asymmetric ligands and where design of these ligands can lead to some really nice catalysis is this asymmetric hydrogenation reaction. So this is a reaction which makes L-DOPA. So L-DOPA is a drug which is used to treat Parkinson's. And this comes from this enamine. So what we're doing here is using this rhodium catalyst down here with this chiral bisphosphine ligand to hydrogenate this enamine here in essentially 100% EE and basically quantitative yield, which you can then just do an acid workup to form L-DOPA. And this, in fact, won the Nobel Prize in 2001 for asymmetric catalysis, and particularly Knowles and Naori were involved in this asymmetric hydrogenation chemistry. And this is all down to kind of exquisite design of this ligand framework. So another example, which I've just pulled out of the literature, is the CN cross-coupling reaction from Mark Sliotto's group, where they use this rather bulky bisphosphine ligand, which enables the CN cross-coupling with this nickel-2 catalyst. And you can access some pretty tricky amines here. So there's some pretty bulky amines and also some bulky alcohols and pretty good yield. So as I mentioned, these reactions wouldn't have been possible without kind of designing these ligands for a certain purpose. And over the years, people have considered about building libraries of these ligands. So libraries to design, discover new, improved catalysts, what's called rational in silico design of catalysts and ligands. These can be used to optimize chemical processes, particularly in the advent of kind of data science machine learning algorithms, and also provide enhanced mechanistic insight. And so one example from the Sigman group a few years ago now, this is also in collaboration with partners at Genentech, was looking at this atroposelective Negishi cross-coupling reaction. So we're coupling this 2-bromopyridine with this aromatic zinc reagent here. And after some modeling where these ligands are featurized, and these are featurized as their palladium dichloride complexes, they come up with this Wolfos type ligand, which gave pretty good selectivity compared to their best case. And this can be readily converted in a few steps to this KRAS covalent inhibitor. And I think since Pint's publication, this reaction was performed on a 500 kg scale. So it shows the power of being able to use featurizing and calculating ligands to predict new ones for a particular process. So these featurizations didn't necessarily include conformers, but bisphosphines can be pretty flexible. And so I've got a couple of examples here, which let's see if I can get it working. So we have ones with an alkyl backbone, which you can see have quite a lot of different conformers. And you compare it to something on the right here, which is probably more rigid in structure. So, and here are some RMSD plots. You basically look at the atom coordinates as a function of conformer, and you can see basically a whole bunch of different conformers here, and then essentially two conformers on the one on the right. And so understanding what these conformers are doing and then subsequently how to featurize them will be pretty important for understanding catalysis. But how do we include that into featurization? So a few examples why they're important before we go into the featurization bit of the presentation is they can affect various properties of ligands. So bite angles, so what's the angle between our donor atoms and our metal? It can affect the buried volume that this ligand takes up. There's also other effects which are related to the substrate. So this is an example from Paul Zimmerman's group. We're looking at the CC bond reductive elimination of these two thiophenes, where we can certain conformers can give you more steric repulsion between these two thiophenes, and also there's pi stacking between the thiophenes and the ligand backbone. Essentially, all these different effects can give you various different pathways, which can change your transition state energy, for example, in a key step. And so this is the figure which was taken out of the paper. The reference is up here, and it shows all the different possible pathways from various reactive conformers to their transition states. And so the energy difference here can be up to about 10 kcal per mole from the lowest conformer to the highest energy conformer. So it can make a real difference in catalysis of what conformer that you are interested in. So there's also this factor of bisphosphine ligands called hemilability. So essentially, this basically means that one phosphorus can come off and come back on to the ligand. So this example is from Stuart McGregor's group from quite a while ago now, but showed computationally that inclusion of this carbon monoxide ligand is possible when one of the phosphines of this bisphosphine ligand comes off to our coordination, and then once it undergoes a migratory insertion with this O-methyl ligand, it can then recoordinate. Another class of ligands which have been around the literature for a while but have gained recent popularity, these bisphosphine monoxide ligands. So this is essentially this is BINAP, but one of the phosphoruses has been oxidized to its phosphine oxide. Essentially, we have the same phenomenon going on. We have the oxygen which can coordinate to our palladium in a kind of bidentate fashion, or it can decoordinate such like this. And the authors of this paper said that this decoordination allowed the formation of this ring in this Mizrachi-Heck cyclization reaction. But essentially, you can imagine a ligand which is quite conformationally flexible. This can affect the properties of a ligand being hemilabile or not. So we wanted to assess the conformal landscape of bisphosphine ligands. And so the Sigman group designed a library of about 617 ligands, and this was reported back in 2023. But we looked at these ligands in terms of the number of conformers that they can have. So this is a chemical space map of the 612 bisphosphine ligands. Essentially clustered this and selected the centroids, and all the centroids are selected or are shown here on the slide. Essentially, we want to give a good variation of ligands across the whole library, so we can look at their conformers. So the conformers were generated using CREST 2.12 from Stefan Grimmer's group, and we used the GFN-FF force field within the program, and we looked at the conformers with a 5 and a 10 kilocalorie per mole energy window. And essentially, it doesn't matter what the ligands are, but each of these bars represents a number of conformers, the blue ones at 5 kilocalories per mole, and the orange ones at 10 kilocalories per mole. You can see we have quite a number of conformers, and also some ligands which don't have that many conformers. But if you work out number of conformers per ligand, it's about 132. And bear in mind, the workflow that we used to calculate the DFT features of these ligands requires one geometry optimization at the DFT level and 2 single point calculations. So this ends up being about 240,000 DFT calculations if we ran through like this. So this process is pretty labor intensive and it takes a lot of time. And one could argue is this a particularly good use of computational resources. Also, something which the community doesn't necessarily talk too much about, but running these calculations does have an environmental impact. So this process requires energy to calculate these ligands and also the CO2 emissions as a result. So we first pruned this list. It turns out CREST generates quite a lot of redundant conformers. So these conformers basically have similar or the same structure. And so we pruned this down using the clustering tool within CREST. So this essentially does a principal component analysis with k-means clustering based on the ligand bite angles. And so you can basically pick the ones which have different structures according to their dihedral angles. And so this does lower the number of conformers down, and so we now have an average of 16 conformers per ligand and about close to 30,000 total DFT calculations. Now, our collaborators at Genentech who are going to be running these calculations asked us, could we reduce the number of conformers down to 10 per ligand? And so we had to think of a way of getting this down to about 10 to find the balance between the representation and on cost of these ligands. So we thought about using a ligand feature in order to do this, one which kind of gives you structural information where you can pick a like dihedral angle, but more chemically specific. And so it needs to be cheap to calculate, like dihedral angle is. The geometries that we use should be close to DFT accuracy, so we know we're getting a good picture of what the ligand structure is. And also it needs to be representative of the changes of the ligand as a function of conformer. And so we looked at these three terms. So what these graphs are showing are the DFT refined structure versus on the x-axis, and the equivalent and the structure directly from crest on the y-axis. And you can see with our cone angle or our solid angle, we have a pretty good matchup between the two axes. So there's good relationship between the two. Similar sort of thing with bite angle, but when we go to our electronic features, we don't see much correlation at all. And we think this is probably because we're calculating these at the GFN level when the electronic features calculated at the DFT level. So there's a mismatch there between the two calculations. But nevertheless, we could probably get away with using some geometric or steric feature to select our conformers. And so we did it like this. So I won't talk about the selection based on the GFN2 energy. Turns out GFN2 energies aren't terribly reliable, and also they miss some conformers if we do it this way. But we used a geometric feature. So bite angle was the one that we ended up selecting, and we did it like this. So we selected the minimum and the maximum value of the bite angle across the ensemble. So you imagine on the histogram like this, we pick this one, and we pick this one at the end, and then equidistant values in between. I'm going to show you a couple of examples of two ligands. One ligand which has 17 conformers here, and the one at the bottom has 55 conformers. And so this is what I was talking about with the energy, how we miss some conformers at the edge. But bite angle, we can get a good spread of bite angle across the whole ensemble, but also keep a good spread of the energy as well. So bite angle was selected, and we could have used easily buried volume to do the same thing. It works just as well, but we selected bite angle because it's been historically quite important for bisphosphine ligands, and this is for two reasons. So this is our Walsh diagram here, one based on a linear platinum L2 complex, where essentially if we move from 180 degrees geometry to something which is tighter, we make the bite angle smaller. What happens to these energies of these orbitals as they increase, and they also change shape. So this particular shape is very important for oxidative addition because it's the right overlap for kind of CX or C halogen bonds. Also, changing the bite angle also affects a thing called a pocket angle. So remember I mentioned at the start about you can generate chiral pockets with these bisphosphine ligands. Well, of course, affecting the bite angle here can affect the size of this pocket, where we have a relatively small bite angle. We have this kind of wide pocket, but when we increase it to 120, we kind of make it kind of well defined. So essentially, the take home here is bite angle reads out a combination of electronic and steric properties, which in our mind for selection of conformers was the ideal feature. So this is an example of why bite angle is important in catalysis. And also bisphosphine ligands in general, actually. So this is a hydroformylation, so it's a little bit like hydrogenation, but we actually have carbon monoxide in there as well, so we can turn alkenes, into aldehydes. So we're looking at is the ratio between the linear and the branched, and so we have these three different wide bite angle Xanthos type ligands, and as you can see, we go between these three ligands that we can increase the turnover frequency or the rate of the reaction, and also get better branch to linear ratios. So not only does it matter in terms of looking at the electronic structure of the metal, but it also makes difference in catalysis. So with this in mind, what we wanted to do is see what it would look like when we looked at our DFT ensembles. So these top graphs you've already seen on the couple of slides ago, but these new ones here show the feature distributions, but these are the DFT calculated ensembles. So basically, we took all the conformers, we refined them using DFT, and so we could simulate effectively what would happen if we selected the conformers based on our byte-angle selection method. So yeah, these bars are the distribution of the features in the DFT, and these red dots are what ligand we would have picked based on our method. And we've got these steric features select. This is the cone angle, the byte angle, NMR chemical shift, and also our HOMO energy. And you can see across all four of these histograms, we have a pretty good distribution of our red dots across our feature ranges. But when we go to an ensemble with the high number of conformers, so there's 55 in this case, you see that we are missing some of the extreme values of these features. But we consider this a good enough trade-off between number of calculations that we run and kind of the overall distribution of these conformers. So using this methodology, we wanted to see what would happen if we put these conformer weighted features. So we're talking about things like maximum conformer value, Boltzmann average, into some historical bisphosphine modeling data from the group. So this first example is a Hiashi-Heck cross-coupling reaction, where we're looking at the coupling between this dihydrofuran and this aryl triflate, and we're modeling the regioselectivity here. So the alkene could be in this position, or it could be in this position, and we're modeling this as delta-delta G double dagger. We come up with this four-component multivariate linear regression model, much like how it was described in the original study, references down the bottom here. But now we're comparing the lowest energy conformer features from our ensemble versus the ones that are conformer weighted. And what these graphs are showing, so this top panel here is showing the density of our modeling errors. The training set in blue and the test set in red. Now, this particular example was chosen because the test set in the previous model that we published showed that some ligands which were further away in chemical space were poorly modeled compared to the ones that were close to the original training set. And so we had the original ligands in blue, and the ones that are further away as the test set. And you can see that we have a modest improvement when we go to our conformer weighted features. We just have a look at our test mean absolute error. We go from 0.51 kilocalories mole, and then this increases when we go to our lowest energy conformer features to 0.69 kilocalories per mole. And you also see that the distribution of these red dots on the bottom here, so these are the individual ligands and displaying their error on the x-axis here. And so we have more ligands in red in our test set, which have a higher error than the ones on the right. And these are the features. It doesn't really matter what the features are for this, but essentially we have three electronic terms, and these violin plots in the bottom here for four ligands. And you can see that some of them have a pretty good wide spread of feature values based on their ensemble, and some of them have different. So we are reading out there's definitely some conformational flexibility that we're putting into our modeling information here. Our second case study was the sulfonilamide carbonylation enantioselect reaction, which goes between this aryl iodide, the sulfonilamide, the presence of carbon monoxide to form these products. And we're looking at enantioselectivity because this reaction produces a chiral center at sulfur. No model was able to be found in the first case study of this reaction, and so this was kind of a really challenging target for us. We ended up using a bit more of a challenging model, right? So rather than using multivariate linear regression, we used a decision tree regression model, but we see the same sort of thing. Going from our conformer weighted features, we have a pretty low test MAE when we compare it to our lowest energy conformer features, and so including conformers in our features for the bisphosphine models, in both cases do show some level of improvement. So very quickly towards the end, I'm just going to buzz through some of the code to do this. So this is all available on the Sigma Group's GitHub in the Bisphosphine conformer selection repository. And so the first thing in this notebook, essentially you set the conformers path. So these are the outputs directly from Crest. It requires one XYZ file per conformer. And then you basically generate a list at the bottom here of the ligand IDs that you want to select the conformers for. So to do this, to generate our features, we're using the Morpheus Python package from Shaoyona at ETH Zurich to collect byte angle, buried volume, and solid angle. But essentially, you can do whatever you want. You can, or whatever package you want, as long as you can calculate the feature, you can put it into this workflow. And we also calculate the XTB energy as well. So this is pretty fast. So this is how it's set up. So we're iterating through the ligands. We're calculating the energies, the byte angles, and the buried volumes. And you'll see it very quickly buzz through all of those features when we run the cell. And there we go, very quickly going through all of the features from Morpheus. This gives you a CSV file as the output, which contains all the information of your selected conformers. No, these are not selected, sorry. These are all the information of all the conformers with all the features. You can then read this back in and use this select equidistant values function to generate the data frame of the selected conformers. Or if you want to go for something slightly more fancy, you can print out the values to the terminal and also give the graphs that I showed you a moment ago as well, which show you the distributions across features and energies. So what we did here was we developed a simple tool, down select our conformers based on our desired geometric feature, which happens to be byte angle. We found this to be a decent balance between conformer ensemble representation and computational cost. There's a few drawbacks, but I think these are okay in the context of the volume of calculations that we were running. And we do see some modest improvement in some modeling outcomes from two examples from our friends at Genentech. So this work was done by myself, Sierra, I think, is on the call, who's now working very hard in kind of rebuilding the bisphosphine library using this methodology. Rich and Kyle are our collaborators at Genentech, and the article describing this, if you want to know more about it, is here. And also, I should mention another complementary approach within C-CAS about looking at bisphosphine featurization and conformers from Olaf's group, which we got involved in to generate some models using these features, which is also on the archive now. That's all I have. Thank you, and I'll happy to take any questions.
All right, thanks, Jamie. Presentation is open for questions.
Hi, Jamie. Amazing work. Thanks for providing some guidelines on how to do this. I wonder, did you compare the benefit of full representation to good representation?
So that again, sorry.
So I think what you showed is like lowest energy conformer is
Yes.
not as good as this selection where you cap everything at 10 conformers for every ligand. Did you on those sets of ligands compute the full ensemble and compare that to the
In the modeling examples, you mean?
Yes.
We didn't do it for the modeling, purely just down to the practicality of the number of ligands. We're talking about 60 odd ligands in there, so there's a lot of conformers. But if we, oh dear, what's going on here? But if I go back to this slide, this kind of answers question, but not fully in terms of modeling complex in a modeling context. But this was where we calculate all of the conformers before we selected, and we use this as the basis to know that because our set of about 12 ligands was pretty diverse across the library. We kind of use this information to say that we are probably going to get a good variation of feature values when we select compared to what we would have from the DFT ensemble. But we didn't do a full analysis on that for the modeling, no.
And do you think like in the Sigman descriptor, what I recall, you have the max, min, and Boltzmann average descriptor. Does the Boltzmann distribution like still stands when you get this kind of sampling of the conformers?
So, I mean, if you want to be the purist, it doesn't technically, because you're not using a full thermodynamic ensemble to do that. And so, the way I think I described it was basically approximation to the Boltzmann average, because you're not getting the full picture of the thermodynamic ensemble. So, it's not a true Boltzmann average, but it's close to being that. I mean, looking at these examples down the bottom here, obviously with this ligand at the bottom here, that will affect the averaging of that term. So no, it's not a true Boltzmann average, but it's an approximation to that.
Thank you.
Yeah, in this other paper that we did together with Jamie, there's a little bit more of a discussion on the point Jules just raised. I mean, what is really the difference of Boltzmann versus low energy versus all the other stuff?
Yeah, and something else which I didn't mention, but it's worth pointing out. You get an absolutely huge explosion of numbers of features when you kind of do this. And so, I mean, Sierra, I think she's on the call. I think we were close to like 2,000 features before we did this modeling, and so we had to do some pretty extensive pruning to make even the modeling not take 3 centuries to run. And so I think when we kind of go through this library again, we're being very selective over what's max, what's min. And so I mean, Sierra's involved in all that analysis, and maybe one day on a call she'll talk about that. But yeah, you have to be very, very careful about this, because the explosions was almost unmanageable without pruning.
Yeah, it gets out of hand pretty quickly.
Are there any perspective on if min max are more important than Boltzmann descriptors?
So gut feeling on this based on some of the data that we've seen. So with electronic features, you can pretty much get away with using Boltzmann average, because the values of the features don't change that much. So the min and the max end up being very similar to the Boltzmann in most cases. The min and the max stuff really comes when you're looking at steric features. So like buried volumes, things like that, and the science paper on Kraken with Abby and Matt, which demonstrates that with monophosphine ligands is a perfect example of where these different min and max features can make a difference.